to engineers' mindset. So let's say we are given a problem and we are asked to do the shear force and bending moment analysis for the beam shown. Okay? So, solution. The first thing is to outline the free body diagram of the beam. Okay, so we recognize that at point A we have a pin, and for the pin support we have double reaction, one vertical, so we call this RAY, also have one horizontal, RAX. At point B there's the 5 kilonewtons force, there's a 3 kilonewtons force. Okay, at point C, between point C and point D, there is a uniformly varying load. And of course, to convert the varying load to point load, you multiply the intensity by the length. So you have 5 by 2, which gives us 10 kilonewtons. And this 10 kilonewtons is placed at the middle of the length covered by the UDL. So middle of 2 is actually 1. 2 divided by 2 is 1. So the point load is kept at the middle of the length covered by the UDL. Have 10 kilonewtons. So from point C to the load is 1 meters. Okay, down to this point is 1 meters. Similarly, at point D, there is a roller support. And for roller support, we have one reaction normal to the surface. So we call this RDY. So that's the free body diagram of the structure. They are all equally spaced, 2 meters apart. So we apply static equilibrium equation. Okay, from static equilibrium equation, summation f of x is equal to 0. So that simply means that all the forces in the x-axis is equal to 0. We have only RDX in the x direction. So RDX is equal to 0. Also, summation f of y is equal to 0. We sum all the vertical forces. So we consider upward force to be positive, while downward force to be negative. So we sum all the vertical forces. We have RAY pointing upward, so it's positive. We indicate RAY. At point D, we have 3 kilonewtons force acting downward, so it's negative. Minus 3. Between C and D, there's 10 kilonewtons force acting downwards, so it's negative. Minus 10. And at point D, we have an upward force RDY, so it's positive, plus RDY. And according to the law, this summation is equal to 0. Alright? So you have RAY minus 3 minus 10 is minus 13, plus RDY is equal to 0. Okay, so let's send minus 13 over to this side of the equation. If negative sign crosses an equal to sign, it becomes positive. So we have RAY plus RDY now be equal to 13. So call this equation 1. So you notice that equation 1 is actually a linear equation with 2 unknowns, which make it impossible for us to find. So the only solution to this, or the only way we can make a break to this, is by applying or taking another word, static equilibrium law, which states that the moment about a point is equal to 0. So we take moment, I will always say, take moment at the point where you have numerous of forces on the beam. So let's take moment at point A. So take moment at point A. Okay, so summation of moment at point A is equal to 0. Let's consider clockwise moment to be positive, anti-clockwise moment to be negative. Alright? So the moment of these two forces, RAY and RAX, at this point is 0. Because moment is force times distance. I've said this over and over. And there is no distance between RAY and RAX at point A. There is no distance between them to point A. So the distance is 0. Therefore, 0 times these forces will give us 0. The next force we can consider moment is what? 3 kilonewtons force at point B. And point B, if I turn this force is acting downwards, therefore the direction of force is pointing downwards. Moment about this point, this force will go towards this direction. So which is what? Positive or assumed direction. So it's clockwise and it's positive. Distance to take the force to get to point A is simply 2 meters. So you have 3 by 2. Similarly, the third kinetic force is pointing downwards. Moment of this force about point A will also move in this direction, point A. So it is also what? Clockwise. And distance to take the third kinetic force to get to point A is simply 1 plus 2 plus 2, which is actually total of 5 meters to get to point A. So we have plus 10 into 5. And finally, we have RBY pointing upwards. Okay? So the moment of this force about point A will go towards the direction because the arrow is pointing upwards, so it will go towards the direction to point A, which is against our moment. It's anti-clockwise from our direction, so it's negative. This is negative. So the distance it takes RBY to get to point A is simply 1 plus 1, 2, 4, and 6. So the total length which is 6. Alright, so we have minus RDY into 6, and this is equal to 0. Okay, 3 by 2 is 6, plus 10 by 5 is 50, minus 6 RDY, and this is equal to 0. Of course, this is 56 minus 6 RDY equal to 0. So we send minus 6 RDY to this side of the equation. Minus plus and equal to sign becomes positive. So we have 56 is equal to 6 RDY. Okay, in order to find RDY, we divide both sides by 6. Okay, so we have RDY is equal to 56 divided by 6, and therefore RDY is equal to 9.3 kilonewtons. Okay, so obtaining that for RDY, we substitute the value for RDY into equation 1. Okay, to obtain RAY. Therefore, RAY plus in place of RDY we have 9.3 equal to 13. Alright, so we send 9.3 over to this side of the equation. Positive sign constant equal to sign becomes negative. Therefore, RAY is equal to, we have 13 minus 9.3. So this simply implies that RAY is equal to 13 minus 9.3 is 3.7 kilonewtons. Alright. So having obtained the values of the reactions, okay, so I said we now bring back the beam. We bring back the beam in the way it is and then place in the values of the reaction so we can do our shear force analysis. Okay, so we bring back the beam. RAY we have here to be 3.7 kilonewtons. At point B, we had a 3 kilonewtons force here. Okay, between C and D, there's a UDL. The intensity of the UDL is 5 kilonewtons per meter. Okay, this is C, B, A, D. At D, we have an upward force of 9.7 kilonewtons. Each of them 2 meters apart. So we start our shear force analysis. Shear force analysis. Okay, so if you've not gone through the introductory video on shear force analysis, please go through it because I gave a breakdown definition of what shear force analysis is. But once more, shear force simply means summation of all the forces acting on the beam stepwise from the beginning of the beam at each point of the beam to the end of the beam, considering upward forces as positive and downward forces as negative. That's what shear force is all about. Now, we also notice that there is a UDL in this beam. This is not an ordinary beam. This beam contains a uniformly distributed load. So there is now a need to form what is called shear force equation, because there is what we call point of contraflexion, and there is what we call point of inflection. I will talk about all that in the subsequent videos. But those 2 points are what necessitates us to form the shear force equation. So there is always a need to form a shear force equation. Whenever there is a UDL or there is a UVL, there is always a need. So when we get there, I will explain to you, and when we start doing more questions, we'll talk more about the point of contraflexion and the point of inflection. Alright, so let's start the shear force analysis. Shear force at point A simply means the force existing at point A. So upward force, remember, is positive, downward force is negative. At point A, we have an upward force, 3.7 kilonewtons, so it's positive. So the shear force at A is simply 3.7 kilonewtons. Alright. This same shear force moves to point B. Alright, so shear force at point B is equal to, we have 3.7 kilonewtons. This same shear force moves from point A to point B, and then at point B it now encounters a downward force. A force that is acting downward, and that downward force is simply 3 kilonewtons. Downward is negative. So we have minus 3 kilonewtons, and this is equal to 0.7 kilonewtons. So the shear force at B is 0.7 kilonewtons. So this same shear force moves from point B to point C. So we have shear force at point C is also 0.7 kilonewtons, because at point C there is no force. But between point C to point D, notice that we have a uniformly distributed load. So there is a need to form what we call the shear force equation. To do this, you take a section. Consider a section from point A somewhere along CD. Let the distance be x from point A. So you consider a section xs. So you section somewhere between C to D. You section somewhere, and you consider that the distance from point A to that point of section is x. So distance from this point to the point of section, you call it x. Okay? You call this distance s. So if the distance from point A to the point of section is x, what now is the distance of what? The UDL. That is from point C to the point of section. We have said a uniformly distributed load is uniform because at each point of the load is the same. So even from point C to the point of section, the load does not change. You see the length 5 kilonewtons per meter. The only thing that has changed now is the distance. So we need to now obtain what is the distance between point C to the point of the section. That's what we are now looking for. From point A to the point of section, we say the distance is x meters. Okay, we say distance is x meters. Therefore, the distance from point C to the point of section, which is now the distance of what the UDL, will now be. Since we are considering from point C to the point of section, it means every other distance behind is left. We don't need to, we just need distance from point C to the point of section. And that distance is simply, since we don't need 2 and 2 from this whole distance x, it means the distance of the section portion of the UDL is simply x minus the distance that we don't need 2 plus 2. We don't need this 2, we don't need this 2, which is 4. So from this point to this point, we don't need it. So it means we don't need 4 meters from what this distance x. So it means distance covered by the UDL is simply x minus 4 meters. So this is the distance of the UDL. X minus 4 meters is now the distance of the UDL. Please take note. This is now to enable us to be able to form the shear force equation because of what the UDL. If there is also a UVL, we will also form the shear force equation. Alright? So like I said, whenever we see the UDL, you take the section very close to the end or any point of the UDL, just take a section but not at the end yet. Alright, so if you take that, we call distance from point A to the point of section is what? X. Now, to obtain the distance covered by the UDL alone, we don't need other distances from this day. We just need from point C to the point of section. So since we are not interested in 2 and 2, knowing that 2 plus 2 will give us 4, we are not interested in this 4 meters. It means we're taking away 4 meters from this x. That will give us the length of the UDL. Okay, in terms of the equation. So having known this, remember the final shear force we arrived at was 0.7. So it is this same shear force that moved from point C and then now encounter a uniformly distributed load. So shear force CD, or at this point we move from point C to point D. You are not yet at D. Shear force CD becomes, remember we had 0.7 kilonewtons left before. So we'll bring it down 0.7 kilonewtons minus, of course, the point load of every UDL is acting downward, so it's negative. So you always put it as negative. Minus, we want to now convert this UDL, the point load. The length of the UDL is x minus 4. Remember, to convert the UDL to a point load, multiply the intensity of the load by the distance covered, or the length covered by the UDL. And in this case now, the length covered by the UDL is x minus 4. So it means the point load becomes the intensity times what length covered. Okay, so we have minus 5 as the intensity, the length covered is x minus 4. So this becomes the load, the point load of the UDL. So this is what we call the shear force equation. This is what we call the shear force equation. Like I said, there's what we call the point of contraflexion and the point of inflection. At each of these points, something happens. I will get there, I will explain better. Alright, but this is called the shear force equation. Okay, so finally, when we get to point D, remember we took a section between along CD, not yet at point D. We took a section along CD and not yet at point D. So when we finally get to D, remember x is moving from point A to the point of section. If x finally gets to point D, it means x becomes the total length of the beam. So if x finally gets to point D, x becomes the total length of the beam. So at point D, x is equal to 6 meters, which is the total length of the beam. X moves from point A to the point of section. If it finally gets to point D, it means it becomes the total length of the beam, which is 2 plus 2 plus 2, that's 6 meters. Therefore, shear force point D is now equal to, we have 0.7, okay, minus 5 into x. Remember now, x is equal to 6. So we have 6 minus 4. Then also notice that at point D, there's an upward force for 7 kilonewtons. Don't forget. At point D, there is also an upward force of 7 kilonewtons, so plus 7. Alright? So this is equal to 0.7 minus 5 into 6 minus 4 is 2. Okay, plus 7. Sorry, 9.7 please. 9.7 kilonewtons. Mistake, 9.7 kilonewtons. 9.7 kilonewtons. Alright. Okay, so we have 0.7 minus 10 plus 9.7 kilonewtons. So shear force at E is now equal to 0.7 minus 10 is simply minus okay, so we said the distance from point A to the point of section is x. So if x eventually gets to point D, it means dx becomes the length of what? The entire length of the beam, which is 6 meters. Okay, so at dx is equal to 6 meters. So shear force at D is now equal to, remember we have 0.7 minus 5 into x is now 6 meters, so 6 minus 4. Okay, now also remember that at point D there is an upward force of 9.3 kilonewtons. Remember that at point D there is an upward force of 9.3 kilonewtons. So so it's positive plus 9.3. Alright, so shear force D is equal to, you have 0.7 minus 5 into 6 minus 4 is 2, okay, plus 9.3. Okay, this is equal to 0.7. 5 times 2 is minus 10 plus 9.3. So shear force D is equal to 0.7 minus 10 is actually minus 9.3 plus 9.3. So which implies that the shear force at point D is equal to 0. Again, remember, at the end of every shear force analysis, you must always have 0 as the answer. Alright, so let's dive into the bending moment analysis. Like I always say, the moment of force at a point is always 0. The moment of this force, 3.7 kilonewtons at point A, is 0 because there is no distance between point A and this force. And force moment is force times distance. Also take note that when you're taking bending moment analysis, always consider upward forces to have positive moment, while downward force should have negative moment. Please do well to watch the introductory video on shear force and bending moment analysis, because I explained all this down there. Alright, so moment of this force about point A is 0. So moment at point A is simply 0. Okay, moving down to point B, the moment of 3 kilonewtons force about point B is 0 because there is no distance between the force and point B. So moment of this force about this point is 0. But before we get to point B, there is a force that means a distance to point B. That force is 3.7 kilonewtons. And distance it takes to get to point B is 2 meters. So since it's upward, we have a positive moment about point B. So the moment at point B becomes 3.7 times 2, and that's equal to 7.4 kilonewtons meter. Okay, moving on from point B, moving on from point B to point C, there is no force at point C. Okay, but we have 3.7 kilonewtons force can make a moment about point C. Also, this 3 kilonewtons force can have a moment about point C. So the moment of this force to point C becomes 3.7 upwards is positive times the distance it takes C to get to point C, which is 2 plus 2, that's 4 meters. Also, we have 3 kilonewtons force about point C is downwards, so you have a negative moment. So moment at point C becomes 3.7 by 4 plus minus 3 kilonewtons by 2. This is equal to 3.7 by 4 is 14.8 minus 6. So this moment, this implies that moment at point C is equal to 8.8 kilonewtons meter. Now, between point C and point D, there is a UDL. So there is also a need to form the UDL bending moment equation at this point. Just like we obtain the shear force equation, there is also a need to obtain the bending moment equation. Okay? So we also consider the same thing we've done. Distance, taking a section from point A, taking a section along CD, and let the distance from point A to the point of section be what? X meters. We've already established that distance covered by this UDL from the point of point C to the point of section is x minus 4. Okay, and you know that moment is force times distance. So the first thing we have to do is obtain the force of the UDL. And of course, the force of the UDL has been established to be 5 times x minus 4, which is the intensity of the UDL times distance covered by the UDL. In this case, is x minus 4. Alright, so we have moment at point D to be equal to, along CD. Moment along CD to be equal to, first of all, the moment of this force about that point of section. Distance from point A to the point of section is x, and moment is force times distance. The force at point A is 3.7, distance to the point of section is s. So therefore, moment of this force about that point of section is simply 3.7 times x. Okay, so we have 3.7 times x. That's the moment of this force about the point of section. Also, from point B to the point of section, what is now the distance? Because we are not moving from point B. Like I told you in the first case, since we are now at point B, it means we are no longer interested in this distance behind, 2 meters. We are no longer interested in this. So it means now that the distance of this force to the point of section is simply, from this force to the point of section is simply x minus 2. It's simply because we are no longer interested in this 2 meters behind, and from point A to the point of section is x. So if we are no longer interested in 2 meters behind, we now want to control from point B. It means we are taking away these 2 meters from what? This distance x. So distance of this force about the point of section is simply x minus 2. Therefore, the moment of this force about that point is simply this force 3 kilonewtons times the distance x minus 2. Please take note. So we have minus because it's pointing downwards. So minus 3 into x minus 2. Okay. And finally, we are between point C and point D. Moment is simply force. So we need to first of all obtain the force. To obtain the force, the intensity of the load times the distance covered by the UDL. And distance covered by the UDL is x minus 4. So the load first is simply minus, because it's pointing downward, 5 times x minus 4. This is the UDL load. This is the load of the UDL, but not the moment. But moment is now force times distance. Remember in the introductory video I said, whenever you convert the point load, whenever you convert the UDL to the point load, place the UDL at the middle of the length covered by the UDL. Please do well to watch the introductory video of point load, UDL and UVL. Do well to watch it. Okay, immediately you convert a UDL to a point load, place it at the middle of the length covered by the UDL. In this case, we've converted this to a point load 5 times x minus 4. The middle of the length covered by the UDL is x minus 4. Middle of x minus 4 is simply x minus 4 divided by 2. Take note of that. That is now the moment. Okay, so you place that middle. So 5 times x minus 4 is the load, then x minus 4 divided by 2. Is now what? Another the distance of the UDL. From that point, you can take moment towards, okay, from the middle, you can take moment to the point of section. Somewhere around here, the point of section. Alright? So this is now the distance it takes to get to the point of section. X minus 4 divided by 2. Okay, so having noted this, this is now what we call the bending moment equation. This is now what is called the bending moment equation. Okay, if this equation is 0, it gives us something which I will explain much better in the further or subsequent questions. Alright, so now notice that at D, x is equal to 6 meters, which is the entire length of the beam. Remember, x comes from point A to the point of section. When it finally gets to point D, it assumes the entire length of the beam, which is equal to 6 meters. Okay, so at D, x is 6 meters. Therefore, moment at point D is equal to, we have 3.7 into 6 minus 8 into 6 minus 2, okay, minus 5 into 6 minus 2 into 6 minus 2, sorry, 6 minus 4 into 6 minus 4 divided by 2. And this is equal to 3.7 times 6 is 22.2 minus 3 into 6 minus 2 is 4, minus 5 into 6 minus 4 is 2, This is actually 2 divided by 2. Of course, 6 minus 4 is 2 divided by 2. This is equal to 22.2 minus 3 times 4 is 12. Minus, this is 1, 2 divided by 2 is 1, 1 times 2 is 2, 2 times 5 is 10. Okay? Alright, so moment at point D is equal to 22.2 minus 12 minus 10 is minus 22, and this is approximately okay, this is equal to 0.2. So we can simply approximate this. To say moment at point D is equal to 0. Approximately, because 0.2 is approximately 0. Again, at the end of every bending moment analysis, you must always obtain 0 as the answer. Alright guys, so we've done the shear force analysis, we've done the bending moment analysis, we now plot the diagram. Okay, so upon plotting the diagram, like I said, always bring out the beam. So we have the beam, we have a 3.7 kilonewtons force at point A, we have a 3 kilonewtons force at point B. Between C and D, there is a UGL worth 5 kilonewtons per meter. This is D, C. At point D, there is an upward force 9.3 kilonewtons. So always trace down all the forces. Trace down all the forces or all the points. Okay, so you make it look like a graph. Alright. So we'll start our shear. Let's start with the shear force diagram. In the shear force we have 3.7, we have 0.7, and we have 0. So the highest value of the shear force is 3.7. So let this be our origin, our 0 mark, 0. 3.7 is the highest, so call it 3.7 kilonewtons positive. So it's upward, it's positive. Followed by 0.7 kilonewtons, also positive, so you should be above the 0 line. So call this 0.7 kilonewtons. And then finally to 0. Finally to 0. So finally to 0. We already have the 0 line. So trace out each of these points. Trace out each of the points. Alright, so moment shear force at point A is 3.7. This is A line, this is 3.7, so you add everything. Okay, shear force at point B is 0.7 kilonewtons. At point B, this is point B, this is 0.7 kilonewtons, so add everything. Shear force at point C is also 0.7 kilonewtons. This is point C, this is 0.7 kilonewtons, so add everything. Finally, shear force at point D is 0. So this is 0 like this point D, you have it. Alright. So the force moves from the origin. Please take note from the origin. Shear force at A is 3.7. So from the origin we get 3.7. This 3.7 kilonewtons force moves to point B and then encounters the downward force that gives us 0.7. So we have 0.7 which is here. This 0.7 force moves down to point C. Between point C and point D, there is a UGL, and I always said the shear force diagram for a UGL is always a slant line. Shear force diagram for a point load is always a straight line, but for a UGL it's always a slant line. So between point C and point D, there is a UGL, so we have a slant line that connects them together. So this is the shear force diagram. So we can as well depict this from the diagram. We have from the origin, we have an upward force, 3.7 kilonewtons from here, so we draw up to 3.7 kilonewtons. This force moves to point B, which is this, and then expresses the downward force of 3 kilonewtons. So downward force of 3 kilonewtons, from this point to this point is obviously 3 kilonewtons because 3.7 minus 0.7 equals 3 kilonewtons. This same force moves to point C, which is here, between C and D will have uniformity there, so we connect it. So this is the shear force that we can shape. Okay, this shear force diagram. So move over to the bending moment diagram. The highest value for the bending moment is 8.8 kilonewtons. That's all. 8.8 kilo. Okay, 7.4 kilonewtons meter. We have 7.4. We have 8.8. So 8.8 is the highest value. Alright, so we draw our zero mark. Okay, these are origin O. So above are positive values, below are negative values. We have 8.8 to be the highest. So let's call it around there. It's 8.8 kilonewtons meter, followed by 7.4 kilonewtons meter. So let's call that 7.4 kilonewtons meter, and then finally to 0. So we trace out each of the points. Trace out each of the points. Moment at point A is 0, indicated here. This is point A. This is 0 line, so as times. Moment at point B is 7.4 kilonewtons meter. This is point B. B is 7.4, so we as times. Moment at point C is 8.8 kilonewtons meter. This is point C. Is 8.8. We as times. Moment at point D is 0. Okay, this is point D. This is 0 mark. We as times. Okay. Now, just like we said, the moment diagram for a point load is a slant line. Now, take note of the difference. The moment diagram, the Shear Force diagram for a point load is a straight line. That's why you have a straight line. For this point load, 3.67 kilonewtons is a point load. This is also a point load, so it comes down. This is also a point load, so just like that. But for moment analysis, the moment diagram for a point load is actually a slant line. It is slant line when it is Shear Force for a UGL, but it is a slant line when it is bending moment diagram for what? A point load. So we connect all the points from the origin. Slant line, connect to point B, connect to point C. Now between point C and point D there is a UGL. The bending moment diagram for a UGL is actually a curve. Okay, so we have something like this. Point G. So we curve down to point D. So this is the bending moment diagram. We have bending moment diagram. Alright guys, I'll come your way again with another amazing question on shear force and bending moment analysis. Till then, subscribe to my channel and of course invite your friends for more subscribers. I will see you in the next videos. Cheers.